Descartes, Descartes, René Descartes, pronounced as Descartes, is best known for the saying, "I think, therefore I am." He is a highly regarded French philosopher, mathematician, and scientist who was brought as the Cartesian plane and analytical geometry, to name a few. We aim to meet the following objectives. For the audience to
be able to identify the possible combinations for the number of positive, negative, and imaginary roots for a given polynomial equation. Grasp the procedure involved in Descartes' rule of sign. Use Descartes' rule of sign as an aid in solving polynomial equations.
Now that we're familiar with René Descartes, we can proceed to learn another one of his great inventions for mathematics, the Descartes' rule of signs. Solving polynomial equations can be hard. You don't have a fixed method to find all the roots, but theorems like Descartes' rule of signs can make solving them much easier for you. You can use Descartes' rule of signs to determine the number of real positive, negative, and imaginary roots. Suppose p of x is a polynomial in standard form with real coefficients excluding 0 and a non-zero constant term. The number of real positive zeros is equal to the number of variations in sign of the terms of p of x, or is less than this number by a multiple of 2.
The number of real negative zeros is equal to the number of variations in sign of the terms of p of negative x, or is less than this number by a multiple of 2.
Simplifying things. To get the maximum number of positive real roots, count the variations in the sign of terms between positive and negative.
Let's use the example x cubed minus x squared plus 2 equals 0. Given p of x equals x cubed minus x squared plus 2, there are two variations in sign, from positive x cubed to negative x squared, and from negative x squared to positive 2.
To get the maximum number of negative real roots, substitute x in the equation for negative x. Simplify the equation. Then, count the variations in sign of the terms in the equation.
In this equation, there is one change in sign, so one variation, from negative x cubed to positive x squared. Let's take down this number in the next column for the table. When applying Descartes' rule of signs, you may be asked to write your answers down in tabular form. In that case, make 4 columns. One for the positive real roots, the negative real roots, the imaginary roots, and the total number of roots. Remember the fundamental theorem of algebra? You'll be using that to determine the total number of roots that the equation has. We now have entries in the first row of the number of positive and negative real roots, as well as the total number of roots. Now, try to think. You needed the number of roots in the first 3 columns to add up the number of roots in the last column. To find the number of imaginary roots, add up the number of roots in the first 2 columns, and subtract that from the total number of roots in the last row. The difference is a possible amount of imaginary roots. The first row serves as only one possible combination of types of roots of the equation. You can now proceed to finding the other combinations. See if you can subtract 2 from the number of positive real roots without the number becoming negative. Remember, you can't have a negative number of roots. 2 minus 2 is equal to 0. Then we retain 1. Add the number you subtracted to the number of imaginary roots. Then the imaginary will be 2. Adding the numbers in the first 3 columns should still add up to the total, and the number of imaginary roots should be even. Repeat the procedure until you can no longer do it. If you can't subtract 2, leave that number be. Now, move on to the next column. Try doing the same thing. Afterwards, try to do the same thing for the first 2 columns simultaneously. Continue to do this until you've exhausted all possible number of combinations.
For our easy question, we are given with the function p of x is equals to x raised to 6 plus 6x raised to 5 plus 15x raised to 4 plus 20x cubed plus 15x squared plus 6x plus 1. We need to determine the maximum positive real roots. Since the signs did not change, we can conclude that the maximum number of positive real roots is 0.
Given p of x is equal to x to the 4 minus 43x squared plus 18x plus 360, determine the possible positive, negative, and imaginary zeros. We count two variations as we have two positive real roots of the first row. Let x be negative. The new function will be g of negative x is equal to x to the 4 minus 43x squared minus 18x plus 360. Two variations as well, thus the maximum possible negative real roots in the first row is 2. Given degree 4, our total is 4. 2 plus 2 minus 4 is equal to 0, thus we have 0 imaginary roots. Repeat the same process until all possible combinations are exhausted.
The difficult question is looking for the possible positive, negative, and imaginary zeros, and solve for the zeros to verify. First, we factor out x because we do not have a constant number, giving us the first root 0. Then we proceed to rule of signs. For positive, there are 4 variations, thus the maximum possible positive real roots is 4. For negative, there are 0 variations, thus 0 possible negative real roots. After that, use the rational root theorem. Now we use synthetic division to come up with the factored function. The final answer is 0, 2 of multiplicity 2, 2i, negative 2i.
There you have it. Descartes' rules of signs is a theorem that allows us to determine the number of real positive, negative, and imaginary roots. To get the maximum number of positive real roots, count the variations of the signs of the terms of p of x. To get the maximum number of negative real roots, count the variations of the signs of the terms of p of negative x. To identify the number of imaginary roots, simply add the number of positive and negative real roots and subtract it from the degree of the polynomial. Take note that imaginary roots come in pairs. The number of imaginary roots will always be an even number. The numbers in the first row are considered the maximum for positive and negative real roots. The actual number may be this number or lower than it by a multiple of 2.